Okay, algebra. Today we are going to work on building quadratic functions from geometric patterns. Tad bit of review. When we first started out the school year, we started talking about linear functions, which were in the form like y equals 3x plus 4, just as an example. It has a y-intercept and a slope. Then we started talking about things like y equals, let's do 2 to the x, and that's exponential. Okay, that's exponential growth. We also had exponential decay. Now we're talking about quadratics, which are in the form of, let's do 5x squared plus x plus 6. Okay, we have an x squared term. What I want to show you is here my first term is x squared, where here my first term is x, where that is linear and this is quadratic. Did you see what I just did? No one's allowed to make fun of me because I'm going to erase it. Quadrat. Still need to erase. Cool. Quadratic. Yep. All right, moving on. Okay, our little warm-up. Figure A is a large square. Figure B is a large square with a smaller square removed. Figure C is two large squares with one small square added. So we need to write an expression to represent the area of each square figure when the side length of the large square is shown in the first column. So right here it'd be 4 times 4. So the area of that large square is 4 squared. So if the square was x times x, it would be x squared. We're going to keep going down that column. If it were 4x, it would be 4x squared, which is the same as 16x squared. And if it were x plus 3, it'd be like this, x plus 3, x plus 3. And all we're going to do there is x plus 3 squared, which really is the same as x plus 3. That 3 looks great, doesn't it? X plus 3. And we'll get to simplifying that later. Cool? All right, so now we're going to go to the area of B. That little square on the inside, the area of that is 1 squared, which is the same as 1. So we're taking the area of A and we're subtracting 1 squared. So really we're doing 4 squared, which is the area of A, minus 1, which is that little circle. Or x squared minus 1. Here we have, you can either do 4x squared minus 1 or 16x squared minus 1. And here we have x plus 3 squared minus 1. Cool? All right, not too bad yet. Now the area of C. We have 2 squares, which are the same as 2 of the figure A's. So it's like 2 of figure A squares. So if I look at the area of C, it's going to be 2 of 4 squared. And I added 1 square. I'm just going to write, I'm going to have a pattern here. That's what I'm going to write. So for this next one, it's just going to be x squared, but I have 2 of them, and I need to add the little square. Next one, we have 2 times, I'm going to use 16x squared plus 1, which is the same as 32x squared plus 1. Because there's two of them. This is 16x squared, and this is 16x squared, and that's 1 squared. So I'm going to add 16x squared plus 16x squared plus 1 squared, which is the same as 2 of 16x squareds, which is the same as 32. Cool. All right, then this last one, I have 2 x plus 3s squared plus 1. Okay, it's really important here. We're sort of building what a quadratic function looks like. All right, we have another pattern. So let's see if we can figure out what's going on with this pattern. It does say, I have step 1, 2, and 3. If the pattern continues, what will we see in step 5 and step 18? Let's see if we can see what we're seeing here. First of all, if I look at step 1, looks like I have 1 square in the middle. I wonder if that's part of my pattern. Step 2, I have 2 by 2 squares in the middle. Step 3, I have 1, 2, 3, and 1, 2, 3 squares in the middle. Pretty cool. Now the outside. It looks like these 4 squares on the outside are pretty consistent. Not pretty consistent, they're actually consistent. So what I see, step 1 gives me a 1 by 1 square in the middle plus 4 squares on the outside. Step 2 gives me 2 by 2 squares on the outside, 2 by 2 squares in the middle plus 4 squares on the outside. And step 3 gives me 1, 2, 3, 1, 2, 3 squares in the middle. It's a 3 by 3 plus 4 squares on the outside. Remember, we're building quadratics here. We talked about what a quadratic is. So what I really have here is 1 squared plus 4. 2 squared plus 4. 3 squared plus 4. Step 5 would be five squares by 5 squares with 4 squares on the outside, which would be a 5 by 5 plus 4. PEMDAS tells us that we multiply first and then we add. We do exponents first and then we add. And then that step 18 would give us 18 squares along one side, 18 along the other, with those same 4, right? So I would have a 18 by 18 plus 4, that's consistent. That's our constant, which is 18 squared plus 4. Cool. So that would be sketch or describe the figure in each of these steps. And how many small squares are in each of these steps? Explain how you know. Well, 1 squared plus 4 is 5 squares. And if you count them, it's 1, 2, 3, 4, 5. And here I've got 1, 2, 3, 4, 5, 6, 7, 8. 2 squared is 4, plus 4 is also 8. 3 squared is 9. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. 9 plus 4 is 13. Because I can't count all my squares. Too much work. I'd have 29 squares there. 18 squared, I don't have memorized, is 324. Plus 4 is 328 squares. Pretty cool. All right, so I need a new slide for 2 and 3. I'll be right back. All right, moving on. Write an equation to represent the relationship between step number n and the number of squares. So we already did this. 1 squared plus 4 is 5. 2 squared plus 4 was 8. 3 squared plus 4 is 13. So what we've done there, we're step 3, we can say n equals 3, n equals 2. It's the number of steps. And then for those, you'd have n equals 5 and n equals 18. So our equation is as simple as saying n squared plus 4, with 4 being the only thing that's consistent in each step. And we call that our constant. Be prepared to explain how each part of your equation relates to the pattern. N equals the number of steps. And then sketch the first 3 steps of a pattern that can be represented by the equation n squared minus 1. So step 1 would be nothing. I'm going to move that. Hold on. Let's go red. Step 1 would be a square that was 1 by 1. Subtract 1, which would be nothing. Step 2 would be a square that's 2 by 2. Minus 1 means we need to, that eraser dot was way too big. We need to subtract 1. So that would be 2 squared minus 1, which is 3, right? Step 3 would be a 3 by 3. But then I need to, let's make my eraser dot a little smaller. Subtract 1. So that one right there is n squared minus 1. For step 3, that would be 3 squared minus 1, which is 8. Okay, 2 squared minus 1, I already did that one, sorry. Is 3, and step 1 would be 0. N squared for step 5. That would be 5 squared minus 1, which would be 25 minus 1, which is 24, etc. All right, let's try another. Here I have sketch the next step in the pattern. What is going on with this one? Looks like step 1, I have 1 by 3. Step 2 is 2 by 4. 1 by 3, 2 by 4. Step 3 is 3 by 1, 2, 3, 4, 5. So step 4 would be 4 by 6. If I only had graph paper. That would be step 4. See, we looked at the pattern for the first 3 steps, and then we tried to replicate the pattern for the 4th step. Kieran says that the pattern is growing linearly because as the step number goes up by 1, the number of rows and the number of columns also increased by 1. Do you agree? Explain your reasoning. So Kieran is correct when he says the number of rows and the number of columns increases by 1. That's correct. But let's go down here. The total number of squares does not increase linearly. Here I have 3 squares, 8 squares, 15 squares, 24 squares. So here I have a plus 5, plus 7, plus 9, not linear. Okay, So the total number of squares does not increase linearly, even though the pattern, the number of rows and the number of columns increases by 1. So not linearly. To represent the number of squares after n steps, Diego and Jada wrote different equations. Diego wrote the equation n times n plus 2. Jada wrote the equation n squared plus 2n. Are either Diego or Jada's correct? Explain your reasoning. Let's just test them. So I'm going to do f of 1. That was 1 times 1 plus 2 using that function. I get an answer of 3. For step 2, f of 2 would be 2 times 2 plus 2. And that gives me a solution of 8, which is correct. F of 3 is 3 times n plus 2. 3 times 5 is 15. So Jada's works. Step 4 would be 4 times 4 plus 2. 6 times 4 is 24. So that does work. Let's try the other equation in green. N squared plus 2n. So for step 1, 1 squared plus 2 times 1 is 3. F of 2 is 2 squared plus 2 times 2. 2 times 2 is 4, plus 4 is 8. F of 3, I wish I had a good place to work. 3 squared plus 2 times 3. 2 times 3 is 6, plus 9 is 15. And then f of 4. Nope. 4 squared plus 2 times 4. That would be 16 plus 8 is 24. So both equations work, and they work because we tested them. Let's talk about why they work in another way. This is our last thing we're doing, so don't give up. N plus 2. And then if I look at n squared plus 2n, I can do what's called factor out the greatest common factor. I can take an n out of that first term and I have an n left. I can take an n out of that second term and I have a 2 left. Okay, these are equal, which also means that I can distribute this, multiply it across, and I get n squared plus 2n. Okay, they are equal. What I like here, if I look at, let's go to yellow. If I look at this function right here, this would be representing my length. Can't read that. N, the first n represents my length. And the n plus 2 represents the height. We'd call it width. Let's just call it width. So length by width. N times n plus 2. So n is 1 plus 2. So n times n plus 2. N is 2. So that's my length. My width is 2 plus 2 is 4. Okay, my length is 3. 3 plus 2. 4. 4 plus 2. So the equation works. Cool, that's it. Good job today. That was a little long.